In this video, I am going to explain the coefficient quantization error. Any filter is fully specified by its coefficient because these coefficient we obtain by following the number of designing steps of the filter from the given specification. So, these coefficient may make the given specification in the design filter. Suppose we designed a IIR filter of the first order and the final transfer function of this IIR filter is this HZ, which is expressed as ratio of two first order polynomials, and the coefficient obtained in this case is 0.538 and 0.999. These coefficients should be stored into the register with infinite precision, meaning is that when we convert this decimal signal into the digital one, we get the 10 bit stream, and this bit stream may be of infinite length. So the actual storage requires the infinite length register. In actual, we have a limit of the register length, so we have to make a compromise in its value. Suppose this compromised value in the stored register is 0.530. So there is an error that we obtain in the actual value and the stored value. This is termed as coefficient quantization error. Coefficient quantization error plays a significant role in the designing of a filter because when we see the frequency response of the design filter that may deviate from the actual response because of this shifting in its coefficient value or because of this error in coefficient value. For example, this can be better understood that this has one pole that lie at the location of 0.999. Basically, this 0.999 is a location just inside the unity circle. And we know that any filter is stable when its pole lies inside the unity circle. So, in actual, it results in a stable filter. But because of the storage, and in the storage we are following the rounding method. So because of rounding, if they exceed from this value in actual, so the stored value may lie on the boundary if it is 1, and if it is greater than 1, it may lie outside the boundary. So in actual, we have designed a stable filter, but because of this finite word length, we are obtaining a filter that is unstable because the pole is in actual lying, in practice lying outside the unity circle. So the coefficient quantization error plays a very important role and it must be considered. Furthermore, the coefficient quantization error is different in case of different structure designing. That can be better understood with the help of this example. In this example, a transfer function is given and we have to design in the direct form 2 as well as in cascade form. When we design it in direct form 2, we have to put the expression of the filter as a ratio of two polynomial. So in this case, the numerator polynomial is 1, so it is 1. So it is 1 in this case, and in here the numerator polynomial, denominator polynomial can be obtained by multiplying these two factors. So we obtain this denominator polynomial, and with this expression we may directly design the direct form 2 structure of the filter, where the coefficients is 0.95 and the coefficient 0.225 here. So now we have to store these two values. When we store these two values, as in the question, it is given b equal to 3 bit. So we have to store only 3 bit of this data. This 3 bit will lead the actual storage of 0.95 as 0.875 and actual storage of 0.225 as 0.125. And when we realize the same transfer function in cascade form, we have to put it in the form of different combination of the poles and zeros. So here we will use it as it is in the designing. Now in this case the coefficient is 0.5. Now after converting, digitizing and rounding and further converting into the decimal value, this will remain the 0.5, whereas this 0.375 will be 0.45. Now we will see the quantization error in the direct form 2 is higher in comparison to the cascade realization. This is the reason that cascade realization is preferred in comparison to the direct form 2 realization, because cascade realization lead to less quantization error, less coefficient quantization error. Thank you.